Hi, good afternoon, everyone, and welcome to our CAWASA Wednesday webinar. This is webinar number 5 for 2026. And this afternoon, we have a special guest who is Mr. Jerry Matteo, who is with WaterTech. He's been a guest on our webinar series previously, and he has attended our CAWASA Operators Conference in St. Lucia in 2019. And we have good connections with his association of Caribda, the Caribbean Desalination Association. So he's one of the experts within the Caribda grouping, and he's going to share with us on the basics of reverse osmosis technologies. Over to you, Jerry.
Thank you very much, Ignatius. Thank you for inviting me, and everyone, thanks for attending. So I called the presentation From Pressure to Purity because you're going to see that we require pressure to create reverse osmosis. Our company, I'm actually based in Puerto Rico. Our company's based here. We have got some engineers and technicians at different points throughout the Caribbean, but our main office is in Puerto Rico. The company name is actually WaterTech Sales and Consulting Inc., long name, but our logo there is WaterTech. So we'll get started.
The slide isn't moving.
No,
Your slides aren't moving?
no.
Oh,
There we go.
yeah, right,
Go back if I can. Okay, I have to use the pad.
right.
Now it's moving. It wasn't there in the beginning.
Okay.
Okay, here we go. And so we're going to talk about theory. And I don't know how many of you run RO systems right now, but if you do, and you've got a lot of experience actually running an RO, you may not have ever seen the theory. And the theory is always interesting to me, and it will help it'll help you run your RO, and it'll help trouble when you the importance of pre-treatment because pre-treatment protects our RO from particles. You're going to see that a little bit about membrane construction, and all throughout the presentation, we'll be talking about terminology or learning some of the terminology. So some of you may already know if you're familiar with reverse osmosis, and it may be new to some of you, but I think it appeals to everyone the way I've laid it out. I've got a lot of slides. If we don't get through all of them in an hour, no problem. Maybe I'll get invited back to go through more of it. So an RO system looks like this. And this is a big one down here on the right and a smaller one here on the left. And these vessels you see here are not the membranes. So our membranes that are going to do the work for us, their membranes are inside these vessels. One of the important components, or one of the most important components I'm circling. I don't know if you, I'm circling the high pressure pump because we're going to need pressure. You're going to see to create pure water through an RO system. This one on the left is probably a beverage. We do a lot of, so our company does a lot of support of reverse osmosis systems throughout the Caribbean. A lot of bottled water companies, beverage companies, food producers, but also this one on the right, I'm sure would be a large desalination facility in one of the islands. So governments would run something like this. Excuse me. So RO is not just desal. That's why I have the title there, RO and desal. It's not just desalinating ocean water. We can use RO in all types of water. This chart, you may have seen it in different forms. It's pretty busy, but let's see if we can sort through it. Down here on the bottom, going to see different process. You'll see that we've got particle filtration. So if you go up from there, you'll see what particle filtration can do. It can remove, way over here to the right, sand. It can remove particles of carbon. dust, coal dust, pollen, different things up to human hair. So most of you, if you I, if you work in wastewater or surface water and potable water, are familiar with particle filtration. A typical example would be a multimedia filter. As we move left to the left down here, we get into finer and finer types of separation or filtration. Way over here to the left, way over to the left is reverse osmosis. Or another one you've probably heard of is ultrafiltration. So if you go up from ultrafiltration, you could see that it can actually take out viruses. It can actually dissolve solids to the left here. Sugar would be dissolved. Um, Salt, sodium chloride would be dissolved. So only reverse osmosis can remove dissolved material. Way over to the right would be particles. Way over to the left would be dissolved matter. So when we talk about RO, it's really one piece of an RO system. You have your raw water, and there'll be unique ways to bring your raw water to your facility. In desal and ocean desalination, this is like there's a whole science behind this. How you're going to bring your ocean water in from and there's all kind of intakes and where you put your intake. You want to minimize sand, excuse me. So there's a whole science behind that. Pre-treatment is really important. We're going to talk a bit about that because pre-treatment protects our RO, but we're going to concentrate mostly here. Also, there's post-treatment. So permeate is the name for the purified water that goes through our membranes. And in some cases, there's actually additional treatment done after the RO, where we might add lime to raise the pH. You can add corrosion inhibitors for your distribution system, etc. But we're going to focus right here mostly. Okay. So raw water, I've heard water called the universal solvent because so many things can dissolve in it. And let's go back. We If you're in, again, wastewater or potable water, surface water treatment, you're obviously familiar with this one up here. You're primarily removing solids, I believe. Wastewater, probably more than that. You might have biological systems, et cetera, to remove some dissolved material. So we primarily have suspended solids and dissolved solids, suspended and dissolved. We also have gases, oxidizers. Chlorine is one. We're adding chlorine. You might even be adding, what else could you add? Bromide or some other oxidizer to kill bacteria. And we've got a lot of biological living organisms that just happen to habitate in our raw water. Wells are pretty clean, but surface water can have a lot, and ocean water has a lot. Up here, I notice I marked this one at the top in red because we want to remove, you're going to see suspended solids through pre-treatment. We do not want suspended solids going to our reverse osmosis. You're going to see that. And we measure suspended solids typically by turbidity. And most of you are probably familiar with a turbidimeter to do that. Dissolved solids we measure as conductivity. The more dissolved solids, the more conductive the water is, or total dissolved solids, which would be like a part per million. So it's just a list of what the suspended solids could be. Talked about microorganisms, silt, clay, colloidal particles. Oh yeah, and so a lot of raw water has dissolved metals in it, but with a little bit of agitation or aeration, just natural, or going through your pumping system, etc., they oxidize and become particles. Iron and manganese. I'm pretty sure you're familiar with those because they, depending on if your raw water source is wells, there's typically iron and manganese in there, or even surface water. So they are typically dissolved in nature, but they oxidize pretty quickly in your treatment plant. So those would all be suspended. And I mentioned that we would typically use a turbidimeter. I'm going to show a photo of one here in a sec, but also for RO, we should measure silt density index. A lot of customers don't. So turbidity is sort of a measure of how many particles I have, or what quantity of particles I have. And then silt density is a better indication of how well we can filter those particles out. Sometimes you can look at this too. So you've got a lot of particles, but
Oh,
what sizes are they and what's the distribution of the sizes? I don't see our customers using this one much. Some use this and almost all. Well, not even all do this, but they certainly should measure turbidity, and we're going to see why. So here's a typical, this is I think a Hawk turbidimeter. Other companies make them. And it's just, I think it's like light refraction. You put your sample in here, you just push a button and it's going to read turbidity. This just shows you here, this is a little bit more about RO. It shows that the lower I go, let me look here, let me see here. Yeah. So the lower I go in with turbidity, um, the less frequently I need to clean my system. So this is cleaning my RO. We're not going to get into cleaning today. That's a whole other presentation, but we do need to clean our RO. And the less particles we have, the less we have to clean. That's the point here. That's what a silt density index meter looks like. This is a little filter cartridge, and you put a little, oh, who makes these? I can't remember the name of the company that makes these little filter papers. You put a filter paper in there of a certain micron size. We're going to draw a vacuum and draw water, time the amount of water, time a certain volume of water to pass through through the filter. And we can calculate what's called silt density index. And it's more an indication of, for example, if you have super, super fine particles, they could blind your filter real quick. And even though maybe it's not a high quantity of particles, they are not good for membranes because they'll blind it quickly and stop the flow. Okay, this is just a little graphic of what an RO system would look like, or can look like, because I put more units of operation in here than you necessarily need on any particular in any particular application or plant. Way over here, this is my little indication of an RO system. That's just one vessel. So you don't see that much, but just that sort of indicates our RO. But way before, almost always when you have an RO system, you're going to have a lot of things in front of it, mostly to protect the RO. So I put a clarifier here because that is one way we can remove suspended solids. And probably most of you, since we're talking to a lot of wastewater people, are familiar with uh, clarifiers. This is just a laminar plate clarifier. And I'm going to show you a photo, I think, of a big plant in Trinidad that uses a clarifier like that. Most don't, but you can. Media is the most common way to remove particles. So all of this here is our pre-treatment. Way over here is our RO system. But this is really, really important. Problems, many problems are resolved by or prevented by pre-treatment. So here's a clarifier, here's multimedia. Carbon, oftentimes you'll see activated carbon filters before an RO system. And these are primarily to remove chlorine. Let me see here. Oh yeah, I put a little note here that you might chlorinate somewhere in here to kill bacteria in your raw water. But chlorine, we're going to see later, can damage the typical type of membrane we use. So we cannot tolerate chlorine. We need to remove it. You can also remove it. Let me see if I have it. No, but you can also remove chlorine. Instead of using a filter like this, you can apply sodium metabisulfite, which is a reducing agent and reduces the oxidizer, the chlorine oxidizer. Coagulants, you're probably familiar with that. So you'd use coagulants here if you had a clarifier. This is actually a filter aid. That's what that indicates. All right, after our carbon filter. So not every plant has all these. I'm just showing what a plant may have. I don't come across this much, but in the Dominican Republic, they use a lot of ion exchange resin before their RO, and this is primarily to remove calcium carbonate to prevent scale on the membranes. But another way to do it, which most people do, is apply, I don't see I have, yeah, an anti-scalant. So if we inject an anti-scalant, we're not going to get into it too much today, but we can also help prevent scale on our membranes. Oh, here's my sodium bisulfite. So if I didn't have carbon, I would use sodium metabisulfite to neutralize chlorine. You could have not always, but typically you've got a holding tank for in this case, it's nice, good, clean filtered water. And then we would get that water over to our RO with a booster pump. Always, you've got a filter cartridge assembly on your RO. It's kind of your final line of defense for particles. And these are more consumable, I call them. Probably most of our customers change their filter cartridges twice a month, right here. And then our high pressure pump. Oops. Our high pressure pump, because you're going to see we need pressure to create water through RO membranes. This is the plant I was talking about. The Salcott you may have heard of. Maybe some of you are from Trinidad that are online right now. The Salcott is a probably system in the Caribbean, maybe even used to be in our hemisphere, one of the biggest, but I know there's some huge ones in California, in Chile now for mining. These are old numbers here, but it started as a 24 million gallon per day plant. I think it's 40 million gallons per day or more. I put it here because I wanted to show you all this here that I'm circling is the pre-treatment. These are clarifiers, right? This is ocean desal, by the way. So they're taking ocean water and uh, drinking, but a lot of it, this complex is in Point Lisas, and that's a big industrial complex. So a lot of the water is used in the industry there. I might turn off if I can. I'm going to turn this off so that, let me see, I'm seeing that I've got not a strong internet connection. So let me know if I bobble in and out. Maybe I can turn off. They say if you turn off your video, it helps. Okay, so the Salcott, inside this big building here are actually the membranes. And this is a phenomenal amount of membranes. I mean, a big RO system might have a couple hundred membranes. This has now 20,000 or more membranes. It's just, this whole building is just full of vessels and membranes. All right, so we talked about suspended solids. Now this is dissolved solids. So in our water, in all types of water, we've got dissolved compounds too. Calcium carbonate in fresh water is one of the more common ones. Silica, sodium, like sodium chloride salt, like ocean water. There's a lot more, manganese, iron that I mentioned before. Oh, there they are. So these are dissolved solids, right? Slide kind of solvents can be dissolved color, pesticides, all can be dissolved matter in water. So I mentioned earlier, we measure dissolved solids in units of conductivity, which is really microsiemens per centimeter or micro ohms, I think that is. So that's just conductivity. That is, so supposedly distilled water doesn't conduct water. So supposedly I could be in a swimming pool of distilled water and lightning strikes and the water won't conduct electricity. So I don't recommend doing that. But the point is that the more dissolved solids, the higher the conductivity, the higher the electrical, the water can conduct electricity and it can be measured by a conductivity meter. The other way to measure dissolved solids is by parts per million. So just but both are used a lot in the industry. Conductivity or total dissolved solids to indicate my amount of dissolved solids in raw and treated water. This is a little bit more about parts per million. I only put this there because people use parts per million a lot and maybe don't know exactly what it means. So it's just a percentage. If I do a weight part per million, if I had one part, what I'm indicating is that I've got 1 pound per 1,000 pounds of water. If I had 1,000 parts per million, I have 1,000 pounds of a particular material. Let's say calcium. So I could have 1 part per million of calcium. That means I have 1 pound of calcium in a million pounds of water. If I had 1,000 here, it'd be 1,000 pounds of calcium in a million pounds. And a lot of times we talk about milligrams per liter. So I just show here the reason milligrams per liter equals a parts per million is because a milligram is 0.001 grams. A liter is 1,000 grams. So if you do the The math on that is the same thing as 1 part per million. Milligram per liter equals 1 part per million. Okay, gases also can be dissolved in our water. Oxygen, hydrogen sulfide. I don't know if you've ever been around a septic well. We do some work in Dominican Republic in Punta Cana. It's a vacation spot, but they take a lot of water out of an aquifer there, and around some of the resorts, there's a lot of hydrogen sulfide in the water. Another reason why I mention this is that dissolved gases pass through reverse osmosis membranes. Reverse osmosis membranes do not remove dissolved gases, and this purchased in Dominican in particular by resorts and hotels and condos, thinking they could get rid of this smell in the water, and they were disappointed to see that they didn't. By RO won't do that. You have to use other treatments to eliminate hydrogen sulfide gas from your water source. So I had mentioned earlier, there's also can be oxidizers. Mostly these are added, right? Oops. Chlorine we add a lot for disinfection. In some of the bottled water plants, they add other things for disinfection. Ozone you could do, or bromine. But all these we have to be careful because thin film membranes, which is the most common membrane in the market and industry, cannot tolerate oxidizers. Only a little bit they can tolerate. So we have to be very careful for our RO membranes. This is an interesting slide. So, we throw around these names here. I'm going to deal with seawater or freshwater or brackish water. And I found this, and I think you might find in the literature these numbers here to be a little bit different, but there's actually some definitions of these four types, these four types of water, and all of these indicate a certain amount of dissolved solid. So we know seawater has a lot of dissolved solids, salt in particular, sodium chloride. It can have up to, I say here 40, but I think there's some places around the world you can have up to 50,000 parts per million of dissolved solids, most of it being sodium chloride. So this would be defined, when we get up this range here, 25,000 above, we have seawater. I know in some of our applications, we're taking water from a lagoon, or even, so we've got brackish water. It's not fresh, it's not seawater, it's somewhere in between. So brackish water is typically defined of water containing between 500 to 10,000 parts per million of total dissolved solids. And then high brackish would even be higher than that. Okay, and fresh water up to about 500 parts. So this slide ties into that last one. This is the United States Environmental Protection Agency recommendations for what's acceptable to drink in terms of dissolved solids. So they're saying that they recommend up to about 500 parts per million. Yeah, parts per million of dissolved solids is acceptable. And down here, way to the left is more ideal. And we'd want 0 to 50 would be great. When you're using membrane technology in ocean water, it's hard to get it down. You need something called a second pass, and then you can get it down. And we'll talk about that in a minute. So average tap water is in here. We could drink higher, and we'd like to be lower to have actually the water tastes better too, because we're going to remove salt and the things. And that's going to be that's the purpose of our RO, is to remove dissolved solids. Oh, this is in Spanish, but it's pretty easy to follow. So way down here at the bottom, this just shows different types of membrane technologies, from micro to ultra to nano to RO. We're not going to get into these too much. I do mention ultra because you hear a lot of that even in the Caribbean, because it's a good pre-treatment for RO. And here to the right, these arrows show, the blue shows what goes through my membrane, and the red shows what doesn't go through my. So, but all of these things don't. Suspended solids don't, bacteria doesn't, viruses don't, and different types of dissolved solids don't, which is good. That's so it's you're going to give us super pure water, but we don't want to use our RO membrane to take out suspended solids. We want either what are these other above? Ultrafiltration is good for that because ultrafiltration will take out the suspended solids, bacteria and viruses too, but it doesn't take out these dissolved solids. So this would be a good pre-treatment here for my RO, right? So just an indication of what goes through and what doesn't go through. So what doesn't go through is called uh, reject, right? Okay, so osmosis. All that was like a kind of a preamble to what we're going into now. So I'm going to read it, but then I'm going to explain a little more. The diffusion of a solvent, in this case, we're talking about water, but it can be milk or other things. There's RO is used to, we'll talk about it in a sec, to actually in the dairy industry. The diffusion of a solvent across a semi-permeable membrane separating two solutions of different concentrations. Okay, so here's my semi-permeable membrane. So suppose I have a membrane here that would allow water to go through, only water, only H2O, and really prevents almost everything else. It would be so like the molecular distribution is so fine that only water molecules can get through. So suppose I have that membrane. On one side, I've got water containing a higher amount of dissolved solids. On the other side, I've got water containing lower dissolved solids. In a naturally occurring osmosis, water, H2O, excuse me, I said that right? Yes, from the right to left. It will not go from the left to the right. When you look at this, you kind of think, and you're looking at this like this potential energy here, this different, water's going to go this way, but it does not. And the reason it doesn't, it's trying to achieve equilibrium. So these two sides are trying to achieve equilibrium. So on the left, I've got this higher concentration. The only way I'm going to equalize with the right is if I dilute it with water from the right side. So that's osmosis. And it's all throughout nature. I was thinking of some examples. Fish use osmosis. So a seawater fish, his skin is a membrane, and remember, we're going to move from lower concentration to higher concentration. They are in a very high. They live in the ocean. The ocean has a high concentration of dissolved solids. Water from these fish will actually leave their body and always is leaving skin. They use their gills to process it and expel the salt. And if they didn't do that, they would dehydrate because water would naturally flow from their flesh into the ocean. And freshwater fish are just the opposite. Freshwater fish are constantly excreting water because they're through their skin, fresh water is passing. Plant roots use osmosis. I was reading this one. So, when you go in water and your fingers shrivel up, that's partly osmosis. They say it's also a kind of I think a nerve response, but you're losing moisture if you're in the ocean. You're losing moisture from your skin into the ocean water because the ocean water is higher concentration. And osmosis says we pass from low to high. Another one, last one would be if you take a vegetable slice, you slice a potato and thin a bowl of salt water, we often say, oh, yeah, that salt just shriveled up the potato, but that is not the case. The fresh water in the potato actually flows into the salt water. And then if we would take that shriveled up potato and put it in fresh water, it'll reverse. Fresh water will pass into it. I think even brining meat, if any of you are chefs or cooks, brining meat, you'd say, well, I'm going to lose the juices of my meat into the brine solution. I believe that does occur. That's why you don't leave it in there for a week. You leave it in there for a certain amount of time, and supposedly you create this cap that once you start cooking the meat, you've created a cap where the very surface of the meat has less fluid, less juice, let's say, and it creates a cap when you cook it. So that's osmosis. Now, the reverse of that is reverse osmosis. So when, okay, so if we want to do the opposite, if we want to take a concentrated stream on the left and we want to force the fresh water out of it through our semi-permeable membrane, we must apply a pressure. And this pressure is in relationship to the amount of dissolved solids that we have in the water. So if we apply a pressure, which is what we do in a commercialized reverse osmosis system, we apply a pressure, and now we can reverse the natural phenomenon of osmosis, and we can drive the fresh water out, and this left side will just get more and more concentrated, and the right side will just be fairly pure water. Some salts will pass through, but not much. Here's a little graphic. I'm just going to, oh, here it goes. It's going to go by itself. I'll start it over. So I think this is going to show osmosis. So we've got fresh water, excuse me, from the right passing into the salty water on the left. And we create the difference here. We create what's called an osmotic pressure. And that is at some point, we will equalize concentrations. And the difference will create a pressure here because we'll have a different level. Actually, this would happen. If we did a little experiment, we would actually have a higher level of water on this left side. And the difference in the two levels is the osmotic pressure created by the amount of dissolved solids in the water that determines how much fresh water passes over to equalize that. So that's osmosis. Going back. In nature, without an applied pressure, we're going to flow from low concentration to high concentration. Osmosis. We apply a pressure and the opposite occurs. We apply a pressure to our concentrated side, our concentrated fluid, and we can actually drive fresh water through the membrane and leave behind very concentrated salts, dissolved solids. So osmotic pressure is related to the amount of dissolved solids in the water. So we got seawater, real high concentration of dissolved solids. The osmotic pressure to just start osmosis would be about, down here's a little formula. It's about one psi per 100 parts per million of TDS. So I just use a number here of 350, 375 psi to start the process of reverse osmosis if we had seawater. If we got fresh water with, say, 1,000 parts per million of dissolved solids, we got less osmosis. So if we don't have that much pressure in these cases, for seawater here, for fresh water there, we won't start to drive the fresh water through the membrane. We don't have enough pressure to overcome the osmotic pressure that's created by the amount of dissolved solids. These are some more photos of what RO systems could look like. I think these are all real. That's a famous soft drink here. This is a power plant, I remember. This might be a power plant too, and this is actually a mining operation there. Okay, the most common membrane used around the world is called the way it's made, the way it's built, it's called a thin film nanocomposite. Well, that's LG, but they're thin film composite membranes. LG has something called a nanocomposite, and they're used in all types of water. Seawater, I think, still exists, but it's you don't see them hardly at all. And interestingly enough, cellulose acetate is tolerant of chlorine, but it takes a super high pressure, so you don't see them. It's very energy demanding. All of them are. When you get into seawater, there's a big energy demand, but a lot less with the thin film composite than with cellulose acetate. Membranes look like this. Oh, it's a little bit distorted, I think, here, because these membranes here on the right, the most common are 8-inch diameter this would be 8-inch diameter by 40 inches long and 4-inch diameter by 40 inches long. They're the most common, but there's even smaller ones. And over here is just a little idea. We won't get into this too much, but inside these membranes is our membrane surface. 30 square feet of membrane surface, 4-inch membranes less. So they make less water. This is kind of what's happening in a spiral wound RO membrane. We've got our feed water coming in here. The fresh water is passing through the membrane sheet as and to the I believe I'm going to show a video that's going to show a little clearer, but the fresh water passes through the membrane because we're applying a pressure back here, and this fresh water, believe it or not, spins all the way around and comes out the center tube. The remaining water just continues down the line to the next membrane, next membrane, next membrane, because membranes are in a line, and it exits the system as concentrate. So our fresh, remember, they're rejected by the membrane, and this stream here is our concentrate stream with all of the dissolved solids, almost all, because a small amount does go through here, but very little. So certain amount here, much more here in dissolved solids, and very little there. This is another way of looking at it. Kind of complicated. I'm going to try to pop a video up here. Hopefully we don't, because I think it's kind of very helpful. This is a little bit more realistic of what a membrane looks like. Again, we got our feed water coming in here. We're going to have this cross flow filtration where our permeate's going to go through the membrane and down around to the center tube, and our concentrated stream with all the dissolved solids just keeps on passing through. Well, sheets are all wrapped around this center permeate tube, and then a 5-fold permeate tube in the center. Through these little, looks like screens, that's where our fresh water would flow into the screen. Permeate would go through the membrane and spiral all the way around to here, and our concentrate would go out the back. Membranes are very thin, that's all this is showing. The membrane itself that actually does the, if you want to call it filtration, it's really more the membrane surface. The molecules are so tight that H2O molecules just pass through the interstitial spaces, believe it or not. But it's just like they say it's like the thickness of paint. So these other layers are backing, polysulfone and polyester fiber. But the membrane itself that does the high-tech work is super thin. Let me see. I'm going to take a chance here. We're doing on time. I'll take a chance and put the video up. Let's see how we do here.
We begin with a product water tube, acting as the permeate collector. Sheets of the permeate carrier are welded to the product water tube. The number of sheets is preset depending on the specific element design. Membrane sheets are folded, barrier sides facing, and feed spacer material is inserted. A bead of glue is precisely applied around the edges of the backside of the membrane sheet. The folded leaf is mechanically inserted between permeate carrier sheets. Successive membrane leaves are assembled and inserted between permeate channels, with glue lines between adjacent leaves, forming a 3-sided envelope enclosing the permeate carrier. Automated fabrication allows more shorter leaves to be assembled in an 8-inch element, compared to fewer longer leaves with manual assembly. During operation, pressurized feed water enters the element scroll through the feed spacer and travels across the surface of the membrane sheet. Water permeates through the membrane into the sealed leaf envelope and flows along the permeate carrier in a spiral direction toward the product water tube. There it is collected and flows out of the element.
Okay, let me go back. Were you all able to see that? Some of you yell no, if not. Okay, I like that. Yeah,
No, the video, Jerry, the video didn't show. Just sorry.
Oh, it did not show.
No.
Okay.
It had this audio, but not the video.
Okay, unfortunately. Well, should I take the time and try to do it again or just keep moving along?
You can try again, sure.
Let me try it again because
Okay.
maybe I didn't share the screen. Oh, let me think. No, it should. All right, I have it up now. And let me see. Do you guys you still see my screen? It says home, recent media. You see that or no?
We begin with a product water tube acting as the permeate collector. Sheets of the permeate carrier are welded to the product water tube. The number of
Now
sheets
it's all blacked out.
is preset depending on the specific element design. Membrane sheets are folded, barrier sides facing, and feed spacer material is inserted.
Yeah, it's still not showing.
It's precisely applied around the edges of the backside of the membrane sheet. The folded leaf is mechanically inserted between permeate carrier sheets. Successive membrane leaves are assembled and inserted in permeate channels with glue lines between adjacent leads, forming a three-sided envelope enclosing the permeate carrier.
I'm afraid, Jerry,
to be assembled in
the video is not coming through.
Okay,
so
let's go back.
to
Yeah, we'll move on. Yeah, that's unfortunate because it explains it better than I could. Okay, we back onto my slides? Can you see my slides?
Yeah, now.
Okay. All right. So we'll explain what the video does a great job, but I'll try to explain it as we move forward. So this representation here, the green represents the pressure vessel where my membranes sit. Light blue, these are membranes. So typically in a seawater system, there are about 7 membranes per vessel. And in a lot of other systems, there's 4 to 6. So you just don't have one membrane. You've got a number of membranes in a line inside of a pressure vessel. Green shows my feed water. My feed water is going to come in. Basically, I've got 3 streams. I've got feed coming in. I've got permeate. That's my clean water that passes through my membrane. I've got concentrate. That's my salts that exit the system. I think I'm going to show it here. Yeah. I'm going to move down to, I'm going to show this. Okay. So we basically have cross-flow filtration to an RO membrane, feed coming in, permeate being created by the water that passes through the membrane itself, and concentrate is the water that, that passes to the next membrane that contains less fresh water, so it becomes more concentrated. I think this is interesting because only the first membrane in an RO system sees my raw water source. So if I have seawater, only the first membrane sees the seawater conductivity. My next membrane sees that water minus fresh water, so it's going to have a lot higher concentration of dissolved solids, a higher conductivity, or part per million of dissolved solids. The next membrane sees even higher concentration, higher, and so forth. And that's important because these last membranes can be problematic. The water in your last membranes in the system are very concentrated, have a very high concentration of dissolved solids, and you can create scale there if you don't use the right helpers like anti-scalants, etc. The front membranes are more susceptible to particles if our pre-treatment didn't take them out, but the final membranes are seeing the highest dissolved solids and are more susceptible to scaling. So related back to pressure, if I have my membranes in a row, and if only the first membrane is seeing my feed water and the last membrane is seeing much more concentrated water, I have an increasing amount of osmotic pressure, right? Remember, osmotic pressure is that pressure that's required to drive water out of a dissolved water source through our membrane, right? So I need a certain amount of pressure here, but I need a lot more here. So what this shows is I need more pressure, this yellow or gold bar. I need a lot more pressure here in the back than in the front. But because of pressure drop, I have less driving pressure. I've got somewhere back here, I've got my high pressure pump. It's applying a certain pressure. In seawater, I think we're going to show it later, we need about 600 to 800 PSI. I don't know if you remember way back, I had a slide that showed you need about 350 PSI or 374 to get osmosis started with seawater. Yeah, but that's only for my first membrane. So if you went into a desal plant, you would see the high pressure pumps, the pressure gauges indicating 600 to 800 PSI because I need enough pressure to drive water out of this last membrane where I've got the highest osmotic pressure. So it's kind of interesting. And that's why I say the theory helps you if you are running an RO. It helps you understand this, why you need certain pressures, why these last membranes are typically more problematic, and why the front membranes maybe have more problems with suspended solids. So every membrane does not see the same water. They all see different water of increasing dissolved solids as we go down the line. We look at that. Okay, another way to show it. So if I have my membrane here, I got my feed water coming in. I only have 3 streams. What comes in equals these 2 that go out. My permeate or product water here, my concentrate or redirect water, or sometimes it's called brine over here. And these 2 have to add up to that. Some people I've seen give me numbers that don't add, but they have to add. So what comes in here, 100 gallons a minute here, I've got to have probably 75 here and 25 there, or 50-50, depending on the water I'm treating. A term called percent recovery is how much permeate I'm making per the amount of feed I'm putting in. So it's what water am I recovering as good, clean product water? It is my permeate or product flow divided by my feed water flow. That is my percent recovery. Oh, good. This slide's right here in the red spot. So depending on my water source and the dissolved solids that it contains, it's going to predict really what's practical to produce in terms of quantity, in quantity of permeate. Seawater we know is really high conductivity, and here they're expressing as milligrams per liter. It's mostly sodium chloride or salt. Freshwater, oh, we've got industrial here. So freshwater can be much lower. They're showing it up to about 10,000. And the industrial water can be all over the map because we can use RO to recover fresh water out of treated industrial water too. So you can see here, this third column, I can only produce about 50%, 45, 50% of the water I put in as clean water in a seawater system. The reason is that last membrane would require so much pressure it wouldn't be practical. So we would exceed the practical osmotic pressure limits to try to produce more water than this. And this is interesting. If you look at this second column and versus the 4th column, we didn't talk much about this, but this is my feed water. The concentrate that passes out of the back of all the membranes is going to be in seawater. The concentration is going to be about double the feed water. And the reason it's double, if 50% of the water, if 50% of the water I feed my system comes out as concentrate, and 50% as good clean permeate, that means that all of the dissolved solids are in half of the water. If that makes sense. All of the dissolved solids are in only half of the water because the other half of permeate has, let's say, virtually no dissolved solids. So all my dissolved solids are in this concentrate half of the water. So mathematically, I double the concentration. What seawater systems do is return this back to the ocean. They send this brine They usually call it brine and seawater. They send the brine or concentrate back to the ocean. You don't want to send it back next to your intake. So you look at the current pattern, etc. You send it back to the ocean so that it's not increasing the dissolved solids in my intake. Okay, brackish water is different. Brackish water, because it's lower dissolved solids, and it's reasonable, we've got a reasonable osmotic pressure to overcome. I can produce more water. I can produce 70 to 85. It's 75 to 80 is a real typical number. So I'm also increasing my brine or concentrate is also much higher than my feed, but it's a whole lot less than seawater. So if we use 75%, if we use a 75% recovery, that means that 75% of the water I put in comes out as permeate, 25% is concentrate. That means that all of my salts are in 25% of the water. So I'd multiply by 4. That's how they're getting this. So if I had a 75% recovery, that means I have 75% good, clean permeate water, fresh water, product water, 25% brine, but all the dissolved solids are in the brine or concentrate. I've got all the solids, dissolved solids, in 1/4 of the water. So my brine quality is 4 times higher dissolved solids than the feed. I hope that's not too much numbers. I happen to love numbers. Okay, so I don't know if this one might be a little complicated. Let's see here. All right, this is just an illustration of kind of what I'm saying. So you got over here to the left in red, 100 gallons in this particular RO. There's my RO system. These are just different vessels. I'm not sure how many membranes are in there. They don't show us, but we've got 100 gallons a minute coming in. There's my filter cartridges that we mentioned, my high pressure pump, because I need pressure to make water through an RO system. I would have only 3 streams, water in, 2 streams out. 1 stream is my permeate. In this case, it's a 1-stage system. We're going to talk about that in a minute. In this case, I've got about half my water produced as good, clean permeate water, right? 100 in, 50 out. And I've got about 50 gallons a minute, 47 as reject or concentrate or brine, right? So in this case, I've got a recovery of 50%, which is about all you could get out of what this is called a 1-stage system we're going to look at in a sec. So seawater systems always look like this. You just have 1 bank of vessels and 1 bank, full of membranes. A 2-stage system looks like this, and I think there's a slide where we're going to emphasize stages again. So on seawater, I have to do this because I'll run out of it. Just the osmotic pressure is too high. I can only recover about 50%, usually 45, 50% of the water as permeate. But if I've got lower dissolved solids in, this would represent a more typical brackish water system. I can actually, in this case, they change the number, but it could be they take a certain amount of feed water in to a similar system that we saw on the previous page, a bank of membranes, and produce a certain amount of permeate, in this case, 100 gallons a minute. But we can take the concentrate or brine to another bank of membranes to get more water out of it. And we can do this because the osmotic pressure isn't so high that we can actually drive more water, even though this bank of membranes, the concentration here is like 4 times that. No, twice that, because about here we have 50%, right? Look here, we've got 100 gallons a minute of permeate here out of 200 feed. If you look back on this previous one, remember we made 50%? Well, here we made 50% again of water, but we take the other 50%, we take the of concentrate and run it through another, in essence, another RO. And we can get 50% out of that. So if we take 100 gallons a minute here, we can get another 50 gallons a minute of permeate, and we can get 150 over 200 is 75% recovery. So here we were able to get 75% of the water we put in out as permeate and only 25% of the water in as concentrate, because we were able to take concentrate to another set of membranes. On seawater, we can't do that, or on something that's water that's really high in dissolved solids. But on fresh water, we can. Okay, so that terminology I'm throwing around because I'm familiar with it. I'm using the terminology of stages. So a stage is when I have, so if you, to A stage is a bank of membranes. So this top illustration is a two-stage system where I'm taking concentrate, not permeate, I'm taking concentrate to another bank of membranes. So both examples, no, this one on the top is a two-stage system. It's two stages because I have two banks of membranes, two separate banks treating different water. The bank to the left is treating my fresh water. The bank to the right is treating the concentrate out of my first bank. That's called a two-stage system. Now, if you notice, I've got 1, 2, 3, 4, 5. I've got 5 pressure vessels in the first stage and 3 in the second. So this would be referred to as a 5-3 array. If you told me, someone says I've got a 5-3 RO, I would know it's a two-stage system. I don't even have to see these words. I would know it's 2 stages because there's a semicolon. I would know there's 5 vessels in the first stage and 3 in the second. That's good terminology to know so that we're all talking the same, language regarding RO. Whoop, back. On the bottom, we've got a 3-stage system, which is also possible with which you need a pretty good water source with fairly low dissolved solids. So here I've got a bank of membranes, concentrate of which is going to another bank of membranes, concentrate of which is going to another bank of membranes. So it's a 1, 2, 3-stage system, 5 vessels here, 3 there, 2 there. It's a 5-3-2 array. If I didn't have either one of these and I only had this one stage, that's a 1-stage system. And you don't even say 5, you just say I have a 1-stage system with 5 vessels. What I didn't show here, though, is because I have too many slides already, so I didn't want to put another one in. So when we talk about treating concentrate from a stage to another stage, or I should say concentrate from a bank of membranes to another bank, those are called stages. But we also could take permeate. We could take permeate from either of these systems and treat it to another RO, and that would be called a pass, a second pass. So if we retreat or further treat concentrate to another bank of membranes, it's called a stage. If we further treat permeate or product water to another bank of membrane, it's called pass. So some of the seawater, well, Dasani water, Dasani's Coca-Cola brand, Aquafina is Pepsi. They actually, those two waters, and probably others out there, but those two I'm familiar with, they take the permeate from an RO, go through another whole RO, that clean water from the first RO to another whole RO, and that's where they make Aquafina and Dasani. And then in those two cases, since they've eliminated all the minerals, they actually add back minerals. But this way they know what they're working with, and they can add a known amount of, they use, I think, potassium, I think magnesium, a few minerals they add back in. So they're taking permeate or product water through other whole separate RO. That's called a second stage. I didn't show it here with illustration, but that's what it is. So it's stages is concentrate, permeate is pass. Ignatius, if we go too long, I know we started a little late because I've got lots of slides, knowing that I wouldn't get through them all. You can just tell me, I'll just sum up.
Yeah, you go ahead. You go ahead.
Okay.
We'll
Okay.
get into
It's
the
just a
10
little too
minutes.
technical. I don't know if it, I'm just, and I'm rushing a little bit because I wanted to get through it, but this kind of presentation, you've got to kind of see it more than once, because some things, you just don't absorb it. But I tried to start out with real basics there. I wish we could have seen the video. We'll have to practice that for another one because that just helps. But the theory of RO sort of sets the stage, and these other slides talk more about what's really going on inside of the system. So here we've got a 2-stage system, a 5-3, right? First stage, second stage, 5 vessels, 3 vessels. We're feeding water. If you look down here in the bottom left, in this case, we're feeding brackish water of 1,000 milligrams per liter, 1,000 parts per million of dissolved solids into, oh, good. This shows all of our vessels have 4 membranes. 1, 2, 3, 4. Remember I mentioned you could have 6, 7, but 4 is common, especially in industry, 4 to 6. So this particular system has 2 stages of vessels, 5 vessels in the first stage, 3 in the second. Every vessel's got 4 membranes in it. Okay, so remember I mentioned that only our first membrane, well, they're showing 2 things here. On this top, back here on the left, on the top set of numbers, they're showing my connectivity. They're using milligrams per liter. My conductivity flowing through my membranes. The numbers below there is the conductivity again, but it's my permeate conductivity that's coming out of the membrane. So only the first membrane, I said it before, I'll say it again, only the first membrane sees my raw water, 1,000 milligrams per liter dissolved solids. My second membrane sees water that's already had pure water pulled out of it. So it's got a higher conductivity, so on and so on. So my last membrane sees higher conductivity. Now, the concentrate from this first bank goes to another bank of 3. So now my next bank of membranes see even higher conductivity, from 1,500 all the way to 2,100, because this is concentrate, right? So you can imagine, now we look at the next row of numbers, the permeate quality gets worse too. So each membrane is making water. Now all the water does combine through the same tube, but the first membrane makes my purest water because it's got, first of all, the highest pressure because I don't have pressure drop there, but also it's got the purest water to work with. My last membrane, way over here to the right, still pretty darn good. I've got permeate water coming out of that last membrane of only 23 milligrams per liter dissolved solids, but it's higher than this 10 over here. Now, when all this blends, I don't know what we'll end up with. Oh, here we go. An average of 18 milligrams per liter in my permeate, and in my concentrate, I've got more than double the dissolved solids of the feed, right? So my salts end up down here in the concentrate. Very little salt passes through to my permeate, but some does. And you could see more passes through from the last membranes because those are seeing higher concentrate water. I think this is kind of interesting. I like this because it wouldn't be, it's like riding a bike, I think. Like, you ever try to, after you know how to ride a bike, you can't even fall over if you want to. But when you're first learning, it's like you don't even know how to keep your balance. Well, this stuff is it's something that should be intuitive, but it's not. But once you see it, then you remember it. Oh, the other thing they're showing here is that my first bank of membranes does make, in total, makes better quality, lower TDS permeate. But it's going to combine with this over here anyway. They're all going to combine into one stream of permeate. I think I got another slide that shows, yeah. So this one shows the similar system, but the pressure profile. So if I've got my feed water pressure, my feed water pump down here to the left, pumping at 265 PSI, my first membrane will see that pressure, but way over here to the right on my second stage, I don't see that pressure because I got pressure drop. So remember, we said we've got higher concentration of dissolved solids, but lower pressure. So I actually make my permeate out of these is not as good, but also I think the slides, yeah, good. We also don't make as much water per membrane as we go down the line. So this slide is showing a flow profile, membrane by membrane. There's my 200 gallons a minute in. It's going to be 40 gallons a minute per vessel, right? Because it's just going to be a kind of one header here that's going to connect all. It's all going to split through 200 divided by 5 is going to split through at 400 gallons a minute per vessel. My first membrane can make me about 4 gallons a minute all by itself. My last membrane way over here on my second stage only makes 3 gallons a minute because I've got less driving pressure, right? Because of pressure drop, and I've got higher dissolved solids, if that makes sense. It's a lot to absorb, but this is the way it works. This is the way it works. That's why the whole title was pressure to purity, because it's all about pressure. Pressure overcoming the osmotic pressure that is that is a function of the amount of the concentration of dissolved solids in my water source. Oh, this one's just to show you that when you look at a multiple stage system, you don't see it as simple as I'm showing it here, like this. You don't see it like that. For compactness, all of the stages are going to be on one skid. So you'd walk up and say, this Jerry Matteo's like crazy. This is just all one stage of vessels. But there are different, like, okay, and here's a blank. So this is actually, you'd have to follow the arrows. A good RO system, especially new, comes with arrows. It'll show you the flow, and you'll see that the fresh water is going through this first stage to the left of five vessels. The concentrate of that is going to these next 3, and the concentrate of that is going to these last 3. So this actually is a 5-3-2. There's 5 first, 3 second, 2 third, but you wouldn't know it walking up to it. It would look like just a one-stage system. You'd have to take time to follow arrows, look for the blanks, etc. Oh, I think that's it. I thought I had more. I might have taken some slides out. So that's what I have. You know, I should have mentioned it. I don't mind questions as we go. So anyone could ask any questions now. Or maybe or we can go back if you want to some slides because I went through it pretty quickly. I was trying to get in on an hour.
Yeah, thank you, Jerry. I know that's very comprehensive, a lot for
Yeah, I mean, I
the
didn't
radio subs
know,
up.
maybe
But
it was
it's
a
all
little
good.
too much
It's all
for.
good. We can have a part two sometime, and you will be able to. We can better prepare for doing the video. So
Yeah, the
that's all
video
good.
just helps show how the water flows. But
Yeah.
yeah.
Any questions, folks?
Does anyone online run an RO now?
Hi, good
You
afternoon.
do.
Timothy Augustus out of
Hi,
Trinidad and
Timothy.
Tobago.
Yeah.
Yeah, so we in our one of our landfills
Oh,
on the swim call, we are in the process of installing an RO system to deal with leachate, to deal with the treatment of leachate.
yeah.
I was just wondering about the maintenance in terms of changing out of the filter. I think you had mentioned how
Yeah.
often in terms of leachate being more a brackish or a high brackish type, how often maybe you have to do that
Yeah.
change?
Well, first of all, Timothy, you're going to find that there's like a lot of times, especially as you go, I don't know where you are in the chain of command, but say the upper management, they spend a lot of money, they approve a project and they get an RO system. And then they're surprised to find out that it takes a lot to maintain it. That you're gonna need chemicals, you're gonna have to change filter cartridges, a lot of things. But what we always start with is a water analysis. So you'd want to, if the fill is already running and you've got leachate you could work with, we would want to analyze that water. And we'd want to look at obviously connectivity, or I should say the total dissolved solids, but you'd want to break it down by dissolved solid. Just measure all the dissolved solids in the water. And that the dissolved solids alone will tell us, we've got actually software that we could plug that analysis into, and it will predict to us. All membrane manufacturers have software. I have here on my slide LG and DuPont, but all of them have software, and they can do a lot of cool predictions to show. Well, that's how someone built this RO. If you already got the RO ordered or it's on its way, somebody hopefully profiled that water to determine what size RO to sell you. So that's one side of it. You may also need an anti-scalant, and that's a different software profile, but you'd want to look at scale potential. So remember, I didn't go over it real specifically, but as we remove fresh water, we're left with all the dissolved solids. At some point, we will exceed the precipitation point, and those dissolved solids will precipitate out as scale. To prevent that, we do a couple of things. We run at the right recovery, so we don't try to pull too much water out, but we also typically use an anti-scalant. So all that can be profiled, but it starts with a water analysis.
Yes, thank you.
Wastewater, unfortunately, is tricky because there's a lot of bio in there. So typically, I don't know so much about, I'm just assuming in a landfill there would be. Is there a whole pre-treatment before this RO? Is there going to be a whole?
Yes, there is. In fact, one of the pre-treatment units would be an oil and water separator.
Yeah.
Because in their preliminary test they would have picked up a lot of oil and fats and so on. So they decided to also have that as part of the system. This is a containerized unit, a 40-foot container.
Yeah, that's exactly right. And so that'd be cool to look at and see what all your components are in there, because wastewater can have all kinds of cats and dogs in it, right? And so your membrane, I hope it came through. We only want the membrane to remove or reject dissolved solids. It's going to plug with all that other stuff. Oil's going to plug it right away. Turbidity is going to, a particle is going to plug it right away. It can also grow by, I didn't talk about it on this presentation, but bacteria will grow a biofilm in there, so we don't want that. So we need to remove that bacteria, but then we have to be careful because if we use chlorine or whatever, that can damage our membrane. So I'm sure a the company that designed the containers built all that in, and they probably a little overkill on the pretreatment. A lot of times you do that on wastewater. So you want to make sure you got some unit in there to cover everything. But this is kind of, I mean, we can help you with this. This is what we like to do. And, all I would need to start would be, we can talk separately, but there's my email if you want to email, but size of the system, flow rates, the number of membranes, the number of stages. I can help you dig through that if you're new to it. And then the water analysis. Someone probably did one. We could start with that. And then that would kick the ball off from there. But you should know, though, be prepared. Membranes need to be cleaned. A good cleaning frequency would be like, say, 4 times a year, maybe less, but you don't want to be cleaning every month. If you are cleaning every month, and these are offline cleanings. You're cleaning every month, and you need to, there's something that can be improved, whether it's a pre-treatment or it's anti-scalant or whatever. So there is a whole cleaning, and your system probably came with a system to clean. So that would be something that is a maintenance item, I guess you'd say. And then filter cartridges, that's a consumable. And if you can get down to twice a month, that's pretty good. But I will say that brand new ROs, when they first start up, usually have problems, just because you have people that are used to running a landfill, not used to running an RO, so they're going to have the learning curve. They'll be, you're just starting up a whole brand new system. So the first couple months, sometimes they go great, but it could be a little bit, nerve-wracking. But you could work through it.
Yes, thank you.
What country are you in, Timothy? Where are you?
Trinidad and Tobago.
Oh, okay. We have an engineer there in Trinidad.
Yes.
Yeah.
Thank you.
Yeah.
Okay, we have a question from Roger Karim in the chat. He says, how does use of beach wells impact on raw water quality?
That's a good one. So, boy, it can depend. But sometimes, what's nice about a beach well, what's good about them, they usually have low turbidity. Because what the problem you can have in an ocean intake is a storm. A storm could kick up so much turbidity you can't even run your RO, even because your pretreatment will be overloaded. You could have sometimes ocean intake is very expensive. You've got to run lines way out there to get clean water. So you typically, oftentimes, you don't run it way out there. You have the intake closer to the land, and you might have passing ships or just currents or things maybe that you didn't account for that can bring in sand. And sand is a killer. The two killers on seawater are particles from sand and also biofouling, because of all the living organisms in ocean water. So beach wells typically are really low, much lower in turbidity. That's good. But I sometimes, well, from an anti-scaling point of view, because what we do is I'm a chemical engineer, we do a lot of the chemical treatment on ROs. Sometimes I call them don't take this wrong, whoever's calling in, but the worst of both worlds, because sometimes the ocean water is going to be primarily salt as your dissolved solid, and salt does not scale. Even as we concentrate, it doesn't really scale my membranes. Beach well could have silica, it could have calcium carbonate, it could have iron, it could have manganese, it could have a lot more minerals than you're going to have in your ocean waters. So you've got to, again, back to Timothy's point and yours, we got to profile that water. You want to see a good water analysis from your beach well. And everything's solvable. You can solve most of the most of the components in the water, you can solve them chemically. You use a good anti-scalant and you profile that. What anti-scalant will take care of these things in my water? But you need good pre-treatment. The beach well going to be typically better on turbidity, so it's more you're more forgiving for your pre-treatment system. So it's probably why they went that way. But they're usually, to me, I don't know, hard to think what I'd rather work with. Maybe I'd rather work with a beach well, but also because I know the chemistry, you're going to need probably more chemistry on a beach well, depending on what other dissolved solids are in there, but more forgiving on less turbidity.
We have another question. Would iron in raw water need pre-treatment?
Okay, that's a good one. Yeah. So I guess the short answer is yes. So because iron oxidizes so quickly, now it's a particle. And we don't want that iron particle going to our membrane. Okay, I should qualify that. It also depends on what level. Our software, our chemical software for RO, will show us using Langelier saturation index. If you give me your water analysis and we see what the amount of iron and manganese are in there, we'll see a very clear graphic that'll show us at various recoveries, depending on how much water I'm trying to make with my RO, where I will start to scale and precipitate that iron in my membranes. And then we can pick anti-scalants and try to keep it in solution. So there are anti-scalants that help keep it in solution, but I think you might be referring to green sand and all those things. If it's high enough, you probably need that kind of a thing. A green sand, or there's something out there, Philox, that's this manganese dioxide, real high concentration manganese dioxide. And I think how that works is both of them, I think they oxidize the ferrous iron to ferric and then they filter it out. So depending on how much iron there is in there, iron can be a killer on membranes. It can be, but it depends on the amount. So it all depends on that. That water analysis is like the beginning of everything for us, where we see what's in there and then we start to battle it from there.
Right. Any other questions? Or okay, there's another one here. How effective is RO at removing microplastics?
That's a good one.
Yeah.
Yes. Well,
Plus, given polymer material the membrane is made from, does it also contribute in microplastics?
No. At the last I would say no. These are good questions. I'm going to bounce these back into a lot of our suppliers because I've not heard this before, but it's a great question. My feeling, but don't hold me to this, it would be that, so the way the membrane works, because I've been corrected by the RO manufacturer. So LG now is called Nano H2O. You see them here on my slide in DuPont. They make membranes, and out there's Hydronautics you're probably familiar with, and Toray. That membrane surface it's basically just molecules in a formation that is so tight that only H2O can pass between those molecules. So everything else is rejected. So my gut feel would be microplastics are rejected. So they'll be in the concentrate. But if they're in the concentrate, we would then, remember I told you in ocean water, we're typically sent, where are you going to send all, let's say you've got a 10 million gallon per day desal system. The concentrate goes back to the ocean. So we'd have to do something. The membrane will probably reject the microplastic, but it'll now be in the concentrate. Where are you going to put 5 million gallons per day of concentrate? So it goes back to the ocean. So that's a very good question, because you can concentrate it in the RO, but you still need a way to get it out of the concentrate. See what I hope you catch what I'm saying. In other words, the membrane will reject it, but it doesn't disappear. Remember, I only have 3 streams: feed water in, good clean permeate product water out, and concentrate out. Concentrate is all of my remaining material that didn't go through the membrane. So even if the microplastic doesn't go through the membrane, it's going to be in the concentrate. Now, in a small system, in a industry, we could probably handle the concentrate some other way. And I do not believe, because it's almost like a line of paint, I do not believe that the membranes add to microplastics, but I never had that question asked before. So I'll dig into that a little more.
Right. All very good questions. And I think we have gone over time now, Jerry, but thank you so much for responding to my request to be our guest at so short notice, and for giving us a very comprehensive presentation. I'm sure I think we had quite a few, people who have remained with us throughout, and apologies for some of our technical difficulties at the start, but you have resumed and we are here. And thank you to Valerie. I know you have a difficult time this week, but keep the faith and keep resting your eyes.
Thanks, Ignatius, and I'll see you next week.
Yeah.
Take care, everybody.
Well,
Well,
everyone,
thank you, Ignatius, and everyone. I
so
enjoy
we're
doing
gonna,
this. I think you can see I enjoy doing it. And I've got a
yeah,
lot of presentations ready. That's why I could respond so quick.
yeah, I know that I've seen, of quite a few of your presentations. I know how passionate and knowledgeable you are about the subject matter. So I thought it was well received and well delivered. Thank you very much, Jerry.
Okay, everybody. Thank you, guys. Thanks,
Bye-bye,
everyone.
everyone. Until
Thank
next
you.
Thank you.
Wednesday.
Take care.
Okay. Bye.
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 Good.